Latex versus mylar. Balloons are wonderful to use as decorations, and we enjoy the buoyancy of them when they're filled with helium. However, latex balloons, we know, have a very brief life that keeps them buoyant and decorating high in the air. Why? Why do latex balloons, when filled with helium, lose their buoyancy? And if filled with air that we exhale, why does it seem to stay at a greater volume for a longer period of time? Well, we're going to come back and address this after we look specifically at effusion. So this video will just remind us of the difference of these specific properties from the perspective of gases, and then introduce an equation known as Graham's law of effusion that has not only lab applications, but industrial applications. So to remind us, diffusion is the spontaneous. It happens without us doing anything, without any outside intervention. Diffusion is the spontaneous mixing of two fluids due to their rapid random motion, where effusion is passage of a gas out a narrow opening in its container. And so we know if this is a rigid vessel with a barrier, that when the barrier is removed, because of the motion of gas particles, we'll eventually have what we could call a homogeneous situation, where here it all depends on the pressure difference of the gas inside of here and here, but also the gas. So it's all probability of when an individual gas particle is going to find that hole and then escape. Okay, so here's just a nice color kind of before and then after diffusion, where this is showing us effusion. Here's just another, I thought these were definitely worth sharing. So this is showing us two separated gases, but then when the initial opening between them is removed or open, and then eventually we're here, if we have this barrier, but with an opening, and of course, the size of the hole makes a difference. This will allow more to pass through depending upon the size of the gas. And I thought that this was good as well. If you want to pause just to take a look at this, just if you're having trouble really understanding the difference of effusion and diffusion, I will move up. I think this is really noteworthy. And also this. And something with that. All right, so hopefully that brings to life for us the difference between effusion and diffusion. Okay, so not sure if in the news you've ever heard the term enriched uranium, as far as the concern that different countries or different types of people are getting a nice amount of enriched uranium. So uranium, of course, is the main fuel, if you will, for nuclear power plants, but also for nuclear bombs. And uranium is typically found in two isotopes, 235 and 238. And the 235 form has been just found to better facilitate the fission that fuels nuclear reactors as well as nuclear bombs. But the problem is that whenever you mine uranium or encounter uranium, that only 0.72% of uranium is this isotopic form. So a method was created that actually separates uranium-235 from uranium-238. And the higher the percentage of uranium-235 in your sample of uranium, the more enriched it is. And ideally, for fission reactions, a 99% portion of uranium-235 is found to be ideal. All right, so how do we do it? All right, Graham's law of effusion. Remember, root mean square velocity. How fast a gas is traveling is dependent upon its temperature, but its molar mass. So we know the greater the molar mass, the lower the speed. Okay, well, really, when we're talking about Graham's law, we're comparing the movement of gases. In fact, the speed, which then influences the rate of effusion. So if we have two gases, and if we just call them gas A and gas B, normally when we're looking at a gas escaping out a narrow hole, we express the amount that's leaving, and usually volume, per unit of time. So we're looking at effusion as a rate, a change in volume per a unit in time. So a rate of effusion could be given in milliliter per second. It could be given in liter per minute, liter per day. All right, so we're expressing effusion as a rate. Now, the rate is definitely dictated by the speed, because the speed, the faster it's going, the more often that gas will find the hole. Okay, remember that speed is inversely related to the square root of the molar mass. So if we are comparing two gases, if we are comparing the rate of effusion of gas A to the rate of effusion of gas B, okay, remember the relationship with speed and molar mass. So the rate of effusion of gas A will be inversely proportional to the molar mass of A square root, and then molar mass of gas B in the numerator. So again, Graham's law of effusion, we are comparing the movement between two gases. So here's our uranium hexafluoride. Now, uranium hexafluoride is normally found as solid or liquid, but it's a volatile compound. So it readily forms a gas. Now, if we have our lightest gas, how fast at the same temperature would hydrogen effuse compared to something of great molar mass as that? Now, depending upon how you set up the equation, now this is saying calculate the ratio of hydrogen and uranium. Now, if it said the ratio of hydrogen compared to uranium or to uranium, I think that would definitely guide us to set up the rate of hydrogen, yeah, compared to the rate of uranium hexafluoride. But this kind of, generic language would definitely have it be acceptable if you flip this. Okay. We would just have different interpretations, which I will go over in a moment. So what we would do to find this ratio, it would be the square root of the molar mass of course, uranium hexafluoride, inversely related, over molar mass square root of hydrogen, which will be 409 gram per mole over 2.02 gram per mole. I would just divide these and take the square root, and the units cancel. And the answer that we got, 14.2. So what that means is hydrogen effuses 14.2 times faster than uranium hexafluoride. Now, if you did the rate of uranium hexafluoride over the rate of hydrogen, it of course would be the inverse, which our answer would be 0.0702, which means uranium hexafluoride effuses 0.0702 times as fast. And so it's slower, if you will, or a much less change in volume per the same unit of time that the hydrogen would. All right, so a difference in molar mass makes a different effusion rate. And so if we go back to this situation, it was genius that an individual figured out that we could use differences in effusion to separate our different forms of uranium. And so if we want to determine the rate of uranium hexafluoride compared to the rate of uranium hexafluoride, but we'll do the 235 version over the 238. They barely differ in their molar masses, but they do differ enough. So we would put 352.04 gram per mole, 349.03 gram per mole, and what we got is 1.0043. Now, that's hardly a difference at all, but enough of a difference. And so if you look up the pictures of how uranium is enriched, there are these huge tanks that are just side by side that they vaporize uranium hexafluoride and then allow it to pass through a single pore opening. And upon a single pass, if we take that effusion rate, you will not be asked to do this calculation, but just to let us know how this works, that's the percentage of uranium-235 in a sample of uranium. Well, one pass increases the percent to 0.723%. And then they put it through again, and they put it through again nearly 1,100 times to get the 99% of the uranium-235 that has been determined to be best for fission. All right, so this problem. If we take a look, they are talking about a particular gas. So that kind of lets me know we don't know what the gas is, and we're given the effusion rate under the same conditions. So that tells us really temperature is the same. The rate of effusion of methane is 47.8 milliliters per minute. What is the molar mass of this gas? All right, so grams of effusion. It's really up to me to set up the equation how I want. But I know I want to find molar mass of this unknown. So I'm going to choose to put my unknown molar mass in my numerator. That's just going to probably save me a step of algebra, that's all. And so that means I put the rate of the unknown here, and then methane. Now, methane has a greater effusion rate. So I already know my molar mass for my unknown is going to be greater than the molar mass of methane. So 1 carbon and 4 hydrogens would be 16.04 gram per mole. Oh, 5, sorry about that. And whenever we do our math, we will find that the molar mass, and so I would divide this and get this to be a single value, 3 sig figs. And then if we, square, well, we'll have this. And then if we square both sides, then we get 3.97 is equal to the molar mass over 16.05 gram per mole, and then multiply both sides. And so our molar mass is 63.7 gram per mole. And again, larger than methane, which makes sense because it's moving, passing out of that single hole a lot slower. All right, those are the kind of problems that we'll have to solve, but also understanding the relationships within Graham's law of effusion. So back to the balloon. When we exhale, mainly we are exhaling carbon dioxide and the nitrogen that we just breathed in. So if a balloon, latex, is filled with this versus helium. Helium, 4 gram per mole. And we could say, 44 gram per mole, 28 gram per mole. So, 44 gram per mole. So these, when you fill a latex balloon with your exhale, these gases are traveling 3 times slower. The rate of effusion will be 3 times less. So these are finding the holes much less than the helium. Now, what makes the Mylar balloons buoyant longer is they have fewer holes. So the helium is still finding the sides of the balloon, but there's not as many holes as the latex for the escape. And so it's trapping it much more efficiently. I hope that you have an understanding more deeply of effusion and can apply Graham's law of effusion.